Assalamualaikum and have a nice day. My name is Damia Zahirah binti Rozi and I am under supervision of Madam Hafiza binti Saad. I will be presenting about my project, which is automated oil palm tree detection using YOLO version 8 based on UAV imagery. Okay, for today's presentation, I will cover 4 main sections, namely background and objective, methodology, results and discussion, and lastly conclusion and recommendation. So let's begin with the introduction of this study. So, as the beginning of an introduction, have you ever wondered how plantation managers monitor thousands of oil palm trees across a large plantation areas? Oil palm plantation plays an important role in Malaysia's agriculture sector, and accurate tree inventory information is essential for the plantation monitoring and the management. With the advancement of UAV technology and deep learning techniques, plantation monitoring can now be carried out more efficiently through automated image analysis. Therefore, this study focuses on the application on the YOLO version 8 object detection model for automated oil palm crown detection using UAV imagery. Traditionally, oil palm tree counting is conducted through manual field surveys. Imagine having to walk across an entire plantation and count every single oil palm tree manually. This process is not only time-consuming and labor-intensive, but it may also induce human errors and inconsistencies. In addition, identifying indoor oil palm trees become more challenging in dense plantation areas where tree crowns overlap with one another. To address this issue, UAV imagery provide high-resolution spatial data for plantation monitoring, while YOLO version 8 offers automatic object detection capabilities for identifying oil palm crowns. Therefore, this study was conducted with two objectives. One is to detect oil palm crown in aerial imagery using YOLO version 8, and the second is to evaluate the oil palm crown detection result using standard performance metrics. Now, let's move on to the methodology. As shown in this workflow, the study consists of several stages beginning with UAV imagery and ending with the model evaluation. The process starts with the generation of an orthomosaic image from the UAV data. The orthomosaic image is then divided into smaller image tiles using the speed rasters tool in the edges. Next, the image tiles are manually annotated and used to train the YOLO version 8 model. Once the model is trained, oil palm crown detection is performed, followed by performance evaluation using standard object detection metrics. The image acquired from an oil palm plantation in Sri Telang, Kuala Lumpur, Pahang, was used as the primary dataset. Before training the model, the orthomosaic image was pre-processed and divided into smaller image tiles of 512 by 512 pixels. This step was important because smaller image tiles are easier to annotate and improve the efficiency of model training. The image tiles were then prepared for manual annotation using the RoboFlow platform. Next, at this stage, manual annotation was carried out using RoboFlow. Bounding boxes were drawn around the individual oil palm crowns to create the ground truth dataset. A total of 37 images were successfully annotated and used for model training. This annotation process is essential because it enables the YOLO version 8 model to learn the visual characteristics and spatial patterns of oil palm crowns from the UAV imagery. Once the dataset was prepared, the annotated images were used to train the YOLO version 8 object detection model. Now, let's look at the detection results. As you can see, the figure is comparison between the model training oil palm crowns and also the YOLO version 8 detection results. The image of the left represents the ground data set, while the image on the right shows the detection models generated by the trained model. As we can see, YOLO version 8 was able to automatically detect and localize multiple oil palm crowns by generating bounding boxes around the detected crowns. This indicates that the model was capable of recognizing oil palm crown patterns from UAV imagery without manual interpretation. However, one interesting observation is that several oil palm crowns were not detected, particularly in dense plantation areas where crown overlap and canopy complexity. So now this is the detection result generated by the YOLO version 8 model. The model successfully identified numerous oil palm crowns and localized them using bounding boxes. However, some crowns remain undetected due to factors such as stem vegetation, overlapping crowns, and the relatively limited size of the training dataset. Nevertheless, the result demonstrate the potential of combining UAV imagery and deep learning techniques for automated oil palm crown detection and plantation monitoring application. Finally, I would like to conclude this presentation. This study, I can say that it successfully developed an automated oil palm crown detection that used the approach of using UAV imagery and the YOLO version object detection model. The proposed framework enabled the detection and localization of oil palm crowns from aerial imagery and demonstrate the applicability of deep learning techniques for this plantation monitoring. I would say that for future improvement, it is recommended to increase the size and the diversity of training dataset, improve the annotation quality and also the consistency, explore more the advance of deep learning architecture and apply the framework to larger plantation areas under different plantation conditions. That is all to conclude my presentation. Thank you for the attention.